Before we begin, please note that the information in this video is for educational and informational purposes only. The potential energy savings and financial outcomes discussed are illustrative and not guaranteed. Every commercial building is unique, and results will vary based on factors like climate, building size, existing equipment, and usage patterns. We strongly advise consulting with a qualified, licensed HVAC professional and a financial advisor to assess your specific situation before making any investment decisions. What if I told you that right now, as you're watching this, there is a silent saboteur in your business, actively draining your bank account every single month? It's not an employee. It's not a competitor. It's a massive energy-guzzling monster that accounts for, on average, 40% of your company's total energy bill. 40%. For many of you, that number is even higher, maybe 50 or even 60%. We're talking about your commercial heating, ventilation, and air conditioning system, your HVAC. It's the single largest operating expense for most American businesses, and for decades, we've treated it like an untamable beast. We just feed it money and hope it doesn't break down in the middle of July. You know the feeling. You get that utility bill in your email. You hesitate for a second before you click it open, and when you do, your stomach sinks. It's higher than last month. Again, you've done everything you were told to do. You've swapped every light bulb for an LED. You've put up signs telling people to turn off the lights. You've even invested in better windows. And yet, that number keeps climbing, a relentless march upwards, eating away at your profits. Feels like you're fighting a ghost. You're trying to solve a multi-$1,000 problem with $5 solutions. And the reason it feels that way is because you've been looking in all the wrong places. The real culprit, the real source of this financial bleeding, has been humming away on your roof or in your mechanical room, operating on technology that is fundamentally catastrophically dumb. Think about it. Your traditional commercial HVAC system is a relic. It operates on a simple binary command, on or OFF. A thermostat on a wall, which is often in the wrong place, gets a little too warm. It sends a panic signal to a giant, powerful rooftop unit. That unit then blasts ice-cold air at 100% capacity into the entire zone, whether it needs it or not. It's like trying to water a single potted plant with a fire hose. It's brute force. It's inefficient. It's incredibly wasteful. It doesn't know if the sun is shining directly on one side of the building, making it 10 degrees hotter than the shaded side. It doesn't know that the big conference room, which was full of 30 people for the morning meeting, is now completely empty. It doesn't know that a cold front is rolling in this afternoon. All it knows is on or OFF. It's a one-size-fits-all solution for a problem that requires surgical precision. And this primitive brute force approach is costing your business a fortune. But what if you could change that? What if you could take that lumbering, inefficient beast and transform it into a finely tuned, intelligent system that thinks for itself? A system that anticipates your building's needs before you do, that makes thousands of micro-adjustments every single day to deliver perfect comfort, using the absolute minimum amount of energy possible. What if you could finally get ahead of that utility bill, not just slowing its growth, but actively forcing it down month after month, unlocking tens, or even hundreds of thousands of dollars in operational savings every year? That is the promise of Smart Commercial HVAC. And over the course of this video, I'm going to pull back the curtain and show you exactly how this technology works. This isn't science fiction. This is happening right now in buildings all across the country. We are not just going to talk about theory. We are going to give you a clear, actionable playbook. You will learn the core components that make an HVAC system smart. You will understand the specific mechanisms, the sensors, the algorithms, the predictive analytics that generate those massive energy savings. And most importantly, you will learn how to evaluate if this is the right move for your business and how to start the conversation with the right professionals. We are going to demystify this technology and turn what seems like a complex, expensive headache into your single greatest opportunity for improving your bottom line. So why is this conversation so critical right now? Because we are at a perfect intersection of three powerful forces: skyrocketing energy costs, massive leaps in technology, and unprecedented financial incentives from both the government and utility companies. The same technology that powers your smartphone, the Internet of Things, has finally come to the world of building management. We now have tiny, affordable wireless sensors that can be placed anywhere, measuring everything from temperature and humidity to occupancy, CO2 levels, and even ambient light. We have cloud computing and machine learning algorithms that can take that fire hose of data and make sense of it in real time. They learn the unique thermal personality of your building. They know that the west-facing offices get hot at 3 p.m. They know that on Tuesdays, the third floor is only at 20% capacity. They can even pull in external weather forecast data and pre-cool or preheat the building during off-peak hours when electricity is cheapest. This isn't just a smarter thermostat. It's a central nervous system for your entire building. It's the difference between a flip phone and an iPhone 15. A flip phone could make calls. That's it. Your old HVAC system can make cold air. That's it. But a smartphone, it's a GPS, a camera, a research library, a communication hub. It integrates dozens of functions into one seamless, intelligent device. A smart HVAC system does the same for your building. It integrates data from dozens or even hundreds of points, and instead of just reacting, it starts predicting and optimizing. Let me paint you a picture. Let's take a typical building manager, we'll call him Frank. Frank's old life was a constant game of thermostat whack-a-mole. He'd get a call from accounting on the 4th floor. "Frank, we're freezing in here." So he'd trudge down to the basement, tweak a manual dial. An hour later, he gets a call from the sales team, right next door to accounting. "Frank, it's an oven in here, can you turn up the AC?" His entire day was spent reacting to complaints, lurching from one crisis to another, all while knowing that the system was running full blast, wasting an obscene amount of energy. He was managing a system he couldn't truly control. Now let's look at Frank's life with the Smart HVAC system. He comes in, sits down at his desk with a cup of coffee, and opens a dashboard on his tablet. He sees a 3D model of his entire building. He can see the real-time temperature, humidity, and air quality in every single room. He sees a red alert that an air handler on the 7th floor is vibrating slightly more than usual, a sign that a belt might be wearing out. The system has automatically generated a work order for his maintenance team to check it before it fails. He sees that the system, having analyzed the weather forecast, has already started to slowly pre-cool the building to avoid the peak demand charges that hit at 2 p.m., a move that will save the company thousands this month alone. Someone from accounting puts in a request through an app on their phone. "Our team is feeling a little chilly today." The system doesn't just blast heat, it analyzes the request, sees that only 3 people are in that specific corner of the office, and makes a tiny incremental adjustment to a local air damper, delivering a small amount of conditioned air just to that area without affecting the rest of the floor. Frank isn't reacting anymore. He's optimizing. He's not just a building manager. He's a strategic operator, armed with data, in total control of his building's performance and his company's second-largest expense. That is the power we're talking about. It's a fundamental shift from reactive chaos to proactive, data-driven control. It's about turning your biggest liability into a strategic asset. So how does this transformation actually happen? How do you give a 50-ton steel box on your roof a PhD in efficiency? It starts by understanding the fundamental difference between a dumb system and a smart one. Think about the traditional HVAC system in most commercial buildings. It's run by a simple thermostat on a wall. That thermostat is basically a caveman with a club. It knows 2 things: too hot and too cold. It has one job: beat the temperature into submission until it hits a single number. It has no idea if 1 person is in the building or 500. It doesn't know that a massive heat wave is rolling in tomorrow afternoon. It doesn't know that electricity costs 3 times as much at 3 p.m. as it does at 3 a.m. It's a purely reactive device, a blunt instrument that costs businesses a fortune in wasted energy and employee complaints. It's like trying to run a modern logistics company using nothing but a walkie-talkie and a paper map. You'll get there eventually, but it's going to be slow, inefficient, and incredibly expensive. Now imagine a different approach. Imagine your HVAC system wasn't a caveman, but an orchestra conductor. Instead of 1 data point from a single thermostat, it has hundreds. It's not just reacting to the temperature, it's anticipating it. It's not just cooling a building, it's managing an entire ecosystem of comfort, air quality, and energy use. This is the world of smart commercial HVAC. At its core, a smart system is a building's central nervous system. It has 3 main parts: the senses, the brain, and the muscles. Let's start with the senses. These are the network of sophisticated sensors placed strategically throughout your building. And we're not just talking about temperature. Yes, you have advanced temperature sensors in every zone, but that's just the beginning. You have humidity sensors because 72 degrees feels very different at 20% humidity than it does at 80% humidity. Controlling humidity can make a space feel more comfortable at a higher temperature, saving immense amounts of energy. Then you have occupancy sensors. These are the game changers. Simple motion detectors or even advanced camera-based systems can tell the HVAC system, "Hey, nobody has been in the East Wing for the last 2 hours. Stop blasting cold air into empty offices." Think about that. How much of your building is empty at any given time? Conference rooms, individual offices, entire floors after 5 p.m. A traditional system cools them all the same. A smart system treats them like the empty spaces they are, saving a fortune. But the real genius is the CO2 sensor. Now, you might think that's just for air quality, and it is. But it's also the single best way to measure how many people are in a room. We all exhale carbon dioxide. The more people in a space, the higher the CO2 level. A smart system uses this data in real time. It can see that the main conference room just filled up with 30 people for a quarterly meeting. It knows that 30 human bodies generate a lot of heat and CO2. So it automatically directs more cool, fresh air to that specific zone to keep everyone comfortable and alert. An hour later, when the meeting ends and everyone leaves, the CO2 levels plummet. The system sees this instantly and ramps down the conditioning for that room. It's not running on a dumb schedule. It's responding to the actual real-time needs of your building and the people inside it. These sensors are the eyes, ears, and nose of your building, constantly feeding information to the brain. And that brings us to the brain, the Building Automation System, or BAS. This is the central command. It's the conductor of the orchestra. It takes in all that data from the hundreds of sensors, temperature, humidity, occupancy, CO2 levels, and it doesn't just react. It analyzes, it learns, and it predicts. This is where the magic happens. The BAS software is connected to the internet. It's pulling in real-time weather forecast data. It knows that a heat wave is expected to peak at 4 p.m. tomorrow. So instead of waiting for the building to get hot and then frantically trying to cool it down during the most expensive energy hours of the day, it starts to pre-cool the building's thermal mass, the concrete, the steel, the walls, early in the morning when electricity is cheap. By the time the heat wave hits, the building is already a reservoir of coolness, and the system can just coast, sipping energy instead of guzzling it. This brain also understands the complex landscape of commercial energy pricing. It knows about demand charges, those massive fees your utility company charges you based on your single highest peak of energy use during a month. The BAS is programmed to avoid those peaks at all costs. It will intelligently stagger the startup of different units and subtly adjust temperatures by a degree or two across the building to shed load and keep your energy usage below that critical, expensive threshold. This alone can slash a commercial energy bill by 20 to 30% before you even account for the other efficiencies. Finally, you have the muscles. The brain is useless without a way to execute its commands. These are the modern high-efficiency components like variable frequency drives or VFDs on your fans and pumps and variable air volume or VAV boxes. Let's talk about VAVs because they are a perfect example of smart execution. A traditional system is like a garden hose with only 2 settings, off or full blast. A VAV system is like having a precision nozzle on that hose. The BAS can tell the VAV box for conference room B to open just 30%, while the VAV for the main, crowded lobby opens to 90%. It delivers the exact amount of conditioned air needed to each specific zone, and no more. This zonal control is what finally solves the age-old office problem of one person freezing while the person in the next office is sweating. It creates a uniformly comfortable environment, which has been proven to increase employee productivity and reduce complaints to zero. Let's go back to our business owner, Sarah. She runs a 40,000 square foot office space. Before, her life was a constant stream of hot and cold calls, thermostat wars, and terrifyingly high summer electricity bills. She felt completely powerless. After installing a smart HVAC system, her reality is transformed. The first thing she notices is the silence. Not just the quiet hum of the efficient machinery, but the silence from her employees. The complaints have stopped. The building is just comfortable. Then she logs into her BAS dashboard on her computer. She doesn't see a confusing thermostat. She sees a dynamic, color-coded map of her entire building. She can see in real time which rooms are occupied. She can see the air quality in the big bullpen. She sees a graph showing the system intelligently pre-cooling the building that morning, completely avoiding the peak demand window in the afternoon. She sees that the system has learned that her accounting department, located on the west-facing side of the building, needs a little extra cooling after 3 p.m. when the sun hits those windows, and it does it automatically. It has learned the unique personality and rhythm of her building. And then, at the end of the month, she gets the energy bill. She braces herself, expecting the usual heart-stopping number. But this time it's different. It's dramatically different. The number is 34% lower than the same month last year, even though it was a hotter month. She didn't just get a new air conditioner. She got a new strategic partner, an automated energy manager working 24/7 to wring every last drop of waste out of her operations. The system isn't just saving her money on energy, it's providing her with something even more valuable: data. She now has a granular understanding of how her building is used moment by moment. This data is the key. It unlocks a whole new level of control and foresight. It's not just about reacting to the present anymore. It's about predicting the future. What if your building could tell you exactly which piece of equipment was starting to fail weeks or even months before it actually broke down? This isn't a scene from a futuristic blockbuster. This is the reality of predictive maintenance, and it's one of the most powerful money-saving revolutions happening inside commercial buildings today. It's a fundamental shift from a philosophy of fix it when it breaks to fix it before it even knows it's sick. To truly grasp the magnitude of this change, let's step into the shoes of a facility manager. We'll call him Frank. For 20 years, Frank has managed a 30-story office tower. And for 20 years, his life has been ruled by what we call reactive maintenance. It's a world of frantic phone calls and unforeseen disasters. Imagine this. It's the hottest week in July. A heat wave is smothering the city. Inside Frank's building, every office is packed. On the 24th floor, a major tech company is about to launch a new product. Their server room humming, cooled by the building's HVAC. Suddenly, Frank's phone rings. It's the tenant on the 24th floor. The air isn't just warm. It's getting hot. Fast. Frank's heart sinks. He sprints to the rooftop mechanical room. The noise tells the story before he even sees it. One of his main chillers, a colossal piece of machinery the size of a small car, is silent. A catastrophic compressor failure. The silence is deafening, and it's the sound of a five-figure problem. Now the chaos begins. Frank is on the phone, calling his HVAC contractor, begging for an emergency dispatch. But it's a heat wave. Every technician in the city is already on a job. He's told it'll be hours, and it's going to cost him a fortune in emergency overtime rates. Meanwhile, the server room on the 24th floor is overheating. The tech company is panicking, threatening to pull their lease. Other tenants are calling, complaining about the sweltering heat. Frank is stuck. He's not managing a building. He's fighting a fire. The eventual repair bill is staggering, but it's a fraction of the total cost when you factor in the potential lost revenue, the damaged tenant relationships, and the sheer stress of it all. This is the old way. It's expensive, inefficient, and completely unavoidable, or at least it used to be. Now let's rewind. Let's give Frank a smart HVAC system. The story doesn't start with a frantic phone call. It starts 6 weeks earlier, with a quiet notification on his tablet. It's an alert from the building's management system. It reads, "Anomaly detected. Chiller Unit 2, Compressor B. Vibration signature has deviated 7% from its 90-day baseline. Acoustic analysis indicates early-stage bearing wear. Estimated time to critical failure, 4 to 6 weeks. Recommended action: schedule non-emergency inspection and bearing replacement." There's no panic, no chaos. Frank sees the alert. He opens the maintenance portal, sees the automatically generated work order, and schedules a technician for next Tuesday during off-peak hours, at a standard, non-emergency rate. The technician arrives, replaces a bearing that costs a few $100s, and is gone in 2 hours. The catastrophic failure never happens. The tenants never even know there was a problem. Frank isn't a firefighter. He's a strategist. He didn't just fix a problem. He prevented a disaster that was weeks away from happening. So what is this magic? How does a building gain this kind of clairvoyance? It's a symphony of 3 core technologies working in perfect harmony. First, you have the sensors. Think of these as the nervous system of your building. In a traditional system, you might have a few basic thermostats. In a smart system, you have hundreds, sometimes thousands of sensors embedded throughout your equipment. They're not just measuring temperature. They're measuring everything. Tiny sensors monitor the precise vibrations of a fan motor, listening for a change in hum that's imperceptible to the human ear. Others track the pressure of refrigerant lines, the voltage and amperage being drawn by a compressor, the humidity in the air ducts, even the sound a machine makes. They are constantly gathering millions of data points, creating a high-definition, real-time picture of your equipment's health, like a continuous EKG for your building. Second, all of this data has to go somewhere. This is where the cloud and the concept of a digital twin come in. Every piece of data from every sensor is streamed in real time to a powerful cloud server. There, the system creates a perfect living digital replica of your physical HVAC system, a digital twin. This isn't just a static 3D model. It's a dynamic simulation that is behaving, aging, and reacting exactly like its real-world counterpart. When you look at the digital twin, you're seeing the precise, live-updated health and performance of your actual equipment. But collecting data and creating a model is useless without the third, and most important ingredient, the brain. This is where artificial intelligence and machine learning come into play. The AI's first job is to learn what normal looks like. Spends weeks, even months just watching and learning. It learns the unique personality of every single piece of equipment in your building. It knows that chiller number 2 hums at a slightly different frequency on a humid Monday morning than it does on a dry Friday afternoon. It establishes an incredibly precise baseline for every conceivable operating condition. Once it knows what's normal, its real work begins. It starts looking for the outliers, the tiny deviations from that baseline. That 7% change in vibration Frank was alerted to? That's not something a human could ever detect during a routine walkthrough. It's a whisper of an impending failure. The AI compares the incoming real-time data against its perfected baseline model, millions of times a second. It's not just looking at one data point. It's correlating dozens of them. It might see that a tiny increase in vibration, combined with a 2% increase in electrical draw, and a half-degree temperature rise on a specific bearing, is a pattern it recognizes. It has analyzed data from thousands of similar machines, and it knows this specific combination of signals is a 95% accurate predictor of bearing failure within a 6-week window. This is the power of predictive maintenance. It transforms your entire approach to keeping a building running. You stop performing maintenance based on a generic calendar schedule, replacing parts that might still have years of life left in them just because the manual says so. Instead, you move to condition-based maintenance. You fix what needs to be fixed precisely when it needs to be fixed. You save money on unnecessary parts, you save money on labor, and you completely eliminate the exorbitant costs and collateral damage of unplanned downtime. And here's the kicker that brings it all back to your energy bill. A failing piece of equipment is an inefficient piece of equipment. That motor with the worn bearing? Long before it seizes up and causes a shutdown, it's struggling. It's fighting against friction. And to do that, it has to draw more and more electricity to produce the same amount of cooling. It's an energy vampire, silently draining your budget for weeks or months before it finally gives out. The AI catches this inefficiency on day one. By flagging that component for an early cheap repair, you're not just avoiding a massive future repair bill. You are immediately stopping that energy waste in its tracks. You're putting money back into your pocket every single hour that the now repaired machine is running at peak efficiency. You are literally turning data into dollars. This level of insight and control is a game changer. We've moved from reacting to emergencies, to preventing them based on a schedule, and now to predicting the future with incredible accuracy. We've given our buildings a nervous system with sensors and a brain with AI. But what if we could give it hands? What if the system could do more than just send an alert to Frank? What if the building could start to heal itself? This is where the game completely changes. Because a building that can heal itself isn't science fiction anymore. It's the reality of modern smart HVAC. The hands we're talking about aren't robotic arms roaming the hallways. They are the thousands of digitally controlled components already inside the system. The actuators that open and close vents, the variable frequency drives that speed up or slow down fans, the valves that control the flow of chilled water. For decades, these were just dumb soldiers waiting for a command. Now the AI brain can command them automatically, with surgical precision, to respond to problems the instant they're detected. Let's go back to Frank, our building manager. In the old world, he gets an alert that the main motor on Air Handler Unit 7, the one cooling the entire accounting department on the 15th floor, has burned out. It's 2 p.m. on the hottest day in August. The temperature on that floor is climbing fast. Phones are ringing off the hook. Frank is in full-blown crisis mode, scrambling to find a replacement motor, paying a fortune for overnight shipping, and scheduling emergency overtime for his technicians. The building is wounded and everyone feels it. Now let's see how this plays out in a self-healing building. It's 3 weeks earlier. The AI brain, constantly analyzing data from its sensor network, notices something Frank never could. A tiny, almost imperceptible increase in the vibration signature of that exact same motor in Air Handler 7. At the same time, it sees the motor is drawing 0.8% more electricity than it should for its current output. To a human, this is just noise in the data. To the AI, it's a whisper of a coming catastrophe. The AI cross-references this data. It pulls up the motor's age, its total run time, the manufacturer's specifications, and even historical data from thousands of similar motors in other buildings across the country. It runs 1 million simulations in a fraction of a second, and concludes there is a 94% probability that the motor's main bearing will fail within the next 30 days. So what does it do? It doesn't just send Frank an alert. It takes action. First, the building begins to heal itself. The AI sends a command to the variable frequency drive on air handler 7, throttling its maximum speed back by just 10%. This reduces the stress on the failing bearing, extending its life. The people in accounting don't notice a thing because the AI simultaneously commands the air handlers on the 14th and 16th floors, and even adjacent units on the 15th to increase their output by a tiny 2%. They work together like a team of surgeons to pick up the slack. They reroute the building's resources to bypass the point of failure, maintaining perfect climate control across the entire zone. The building has effectively put its own motor on light duty without anyone even knowing. Second, the system uses its hands to help Frank. It doesn't send a cryptic error code. It automatically generates a detailed work order in Frank's maintenance software. The ticket reads, "Preventative maintenance required. High probability of bearing failure in air handler 7 motor. Model number XYZ. Recommend replacement within 21 days. Part number is 123 to 456. The system has already checked the inventory of 3 local suppliers, found the part in stock at the best price, and attached a purchase link to the ticket. It even analyzed the building's occupancy schedule and suggested 3 optimal times for the repair to be done. When the 15th floor has the fewest people, minimizing disruption. This is the difference between reactive and predictive. One is a frantic, expensive emergency. The other is a calm, scheduled, low-cost repair. This isn't just a fantasy. This is a technology called Automated Fault Detection and Diagnostics, or AFDD. Think of it as a team of expert engineers living inside your building's control system, working 24 hours a day, 7 days a week. They never sleep, they never take a vacation, and they see everything. AFDD is the engine that drives this self-healing capability. It's a master of pattern recognition. It understands the intricate relationships between every component in your HVAC system. For example, it knows that if a specific valve is commanded to be 50% open, and the airflow sensor downstream is only reading 20% of the expected volume, there's a problem. But it doesn't stop there. It then looks at the pressure sensors, the fan speed, and the temperature coils. Is the fan drawing more power? Maybe the air filter is clogged. Is the pressure differential wrong? Maybe a damper is stuck closed. The AI is a detective piecing together clues from dozens of data points to not only tell you that there's a problem, but to tell you what the problem is and where it is with incredible accuracy. This solves one of the biggest energy vampires in commercial buildings: hidden faults. A single damper stuck in the open position, pumping cold air into an empty storage closet all winter long, can waste thousands of dollars. A slowly leaking valve in a chiller can go unnoticed for years, driving up electricity costs month after month. These are the silent killers of your energy budget. Humans often don't find them until they cause a major, catastrophic failure. But an AFDD system finds them in days or even hours. And the savings are staggering. The U.S. Department of Energy estimates that this kind of intelligent fault detection can reduce HVAC energy waste by 20 to 30%. Let me say that again, 20 to 30%. For a large office tower or a hospital campus, that can translate into hundreds of thousands or even millions of dollars in savings every single year. On top of that, by shifting from emergency repairs to predictive maintenance, businesses see an average reduction of 15 to 25% in their overall maintenance budget. The parts are cheaper because they aren't rush ordered. The labor is cheaper because it isn't overtime. And the biggest saving of all is the one you can't always put a number on: the cost of angry tenants, lost productivity, and damaged reputation when the system fails. So we've given our building a nervous system of sensors and AI brain to think, and now a set of hands to act and even heal itself. It's a marvel of proactive efficiency. The building is no longer just a static structure. It's a responsive organism, constantly working to keep itself healthy and optimized. It's maintaining the perfect temperature, based on the schedule it was given: 72 degrees from 9 to 5, Monday through Friday. But here's the next billion-dollar question. What if that schedule is wrong? What if the entire sales team is at an off-site conference on a Wednesday? Why are we spending a fortune to perfectly cool 50 empty desks? The building is healthy, but is it smart enough to be aware? The next leap in intelligence isn't just about the building's health. It's about its awareness of the people inside it. It's about evolving from a fixed schedule to a living, breathing system that adapts in real time to you. This real-time adaptation is the difference between a dumb tool and an intelligent partner. Think about the old way, the way things still are in 90% of commercial buildings today. An HVAC system is programmed on a simple timer. Monday to Friday, 7 a.m. to 6 p.m., the system is on. Full blast. Saturday and Sunday, it's off. It's a blunt instrument. It has no idea if there's a holiday on Monday. It has no idea if the entire company is off-site for a corporate retreat on Wednesday. Just knows the schedule. So it dutifully chills an empty 20-story office building to a perfect 72 degrees, burning thousands of dollars because a calendar told it to. It's like paying a full-time salary to an employee who only shows up half the time. It's madness, but it's been the standard for decades. The first step away from this madness was the humble motion sensor. You've seen them everywhere, those little white plastic domes on the ceiling or high on a wall. Most of them use something called passive infrared or PIR. In simple terms, they're not looking for movement, they're looking for heat. Your body is a walking, talking radiator, constantly emitting infrared energy. When you walk into a room, the PIR sensor detects this sudden change in heat signature and says, "Aha, someone's here." The lights click on, and the HVAC system gets the message to start conditioning the space. It was a revolutionary idea. For the first time, the building wasn't just following a schedule. It was reacting to a person. But it was a clumsy reaction. The PIR sensor is a 1-bit system. It can only answer one question. Is there a heat source moving in this room? Yes or no? It can't tell the difference between one person working late at their desk and a 30-person team collaborating on a project. To the system, it's all the same. So, that one person gets the same amount of air conditioning as 30 people would, which is incredibly wasteful. Furthermore, if you sit too still for too long, as we all do when we're deep in focus, the sensor decides you've vanished. The lights go out, the air stops flowing, and you're left waving your arms around like a lunatic to let the building know you still exist. Technology, of course, evolved. We got ultrasonic sensors that bounce high-frequency sound waves off objects to detect presence, which were better at catching small movements but could sometimes be fooled by a curtain rustling in the breeze. Then came dual-tech sensors, combining both PIR and ultrasonic, a belt and suspenders approach to make sure the room was truly occupied. These were better, more reliable, but they were still stuck answering that same simple question, yes or no. Occupied or unoccupied? The building was aware, but its vision was blurry. It could see a shape in the dark, but it couldn't make out the details. The true quantum leap, the technology that is fundamentally rewriting the rules of energy management, is the ability to move beyond simple detection to actual counting. This is where Smart HVAC gets its superpowers. Instead of a simple motion detector, imagine a sophisticated optical sensor mounted on the ceiling. This isn't a security camera recording faces. Let's be very clear about that because privacy is paramount. These systems are designed to anonymize. Some use thermal imaging, seeing people as heat signatures like something out of the movie Predator. Others use advanced computer vision to identify human shapes as abstract blobs or stick figures. The system doesn't know or care if you're Bob from accounting or Sarah from marketing. It only cares about one thing. How many of you are there? 1517? Suddenly, the building isn't just seeing yes or no. It's seeing with perfect clarity. That conference room on the 3rd floor doesn't just have people in it. It has 12 people in it. The open plan office on the 5th floor isn't just occupied. It has 47 people in it. And the executive suite on the top floor has exactly one. This data is gold. But it gets even smarter. The building doesn't even need to see you to know you're there. You're carrying the evidence in your pocket. Your smartphone, your laptop, your smartwatch, they are all constantly pinging the local Wi-Fi and Bluetooth networks. Advanced systems can now anonymously count these devices within a specific zone. By analyzing the number of unique signals, the building can develop an incredibly accurate, real-time census of its population, room by room, floor by floor, without a single camera. It's listening to the digital heartbeat of the building. So, what does the HVAC system do with this newfound omniscience? It performs magic. It unlocks a strategy called demand-controlled ventilation, or DCV. And this right here is one of the single biggest energy-saving opportunities in any commercial building. See, a huge portion of an HVAC's job isn't just cooling or heating the air that's already inside. It's pulling in fresh air from the outside, conditioning it, and then circulating it to keep the indoor air quality high and prevent CO2 levels from rising. The old way was to pump in a fixed amount of outside air based on the theoretical maximum number of people the room was designed for. That big conference room designed for 50 people? It was getting enough fresh air for 50 people all day long, even when it was empty. It's like ordering a feast for 50 people 3 times a day just in case they all show up for dinner. With occupancy counting, that all changes. The smart system knows there are only 12 people in that conference room right now. It calculates the exact amount of fresh air needed for 12 people to be comfortable and healthy, and it provides precisely that much. Not a cubic foot more. When 5 people leave, it dials the ventilation back. When 3 more enter, it ramps it up. It is constantly matching the ventilation load to the actual human load in real time. The energy savings from no longer having to heat or cool all that unnecessary outside air are staggering. We're not talking about 5 or 10%. We're talking about potential reductions of 30, 40, even 50% or more in ventilation energy costs. Let's put this into a story. Imagine a 10-story corporate headquarters, Future Corp. Before, their building ran on a schedule. At 7 a.m., the entire 200,000 square foot building roared to life. By 8:30 a.m., it was a comfortable 72 degrees from the lobby to the top floor. But on this particular Tuesday, the entire sales team, all 50 of them who work on the 4th and 5th floors, are at an off-site conference. In the old system, those 2 floors would be cooled and ventilated all day long for a ghost crew. A complete waste. But Future Corp has a smart system. At 7 a.m., the system sees 0 people on floors 4 and 5. It keeps those floors in a deep setback mode, just circulating the air gently. It sees the engineering team arriving on the 8th floor and directs cooling there. It sees the marketing team gathering in the big project room on the 3rd floor and ramps up the ventilation specifically for that zone. The rest of the building remains in a low-power state. At lunchtime, it sees a massive migration to the cafeteria on the ground floor. It anticipates this, pre-cooling the area just before noon and pumping in fresh air to handle the crowd. Meanwhile, it dials back the now empty office floors, saving a fortune. In the afternoon, a small client meeting happens in a single conference room on the ghosted 5th floor. The system doesn't turn on the whole floor. It creates a microclimate, a perfect bubble of comfort just inside that one room, leaving the surrounding 20,000 square feet untouched. When 6 p.m. rolls around, the old system would shut off, plunging anyone working late into a stuffy, uncomfortable environment. The smart system sees the 3 accountants on the 9th floor racing to meet a deadline. It maintains perfect conditions just for their section of the office, while allowing the other 99% of the building to go to sleep. Future Corp isn't just saving money. They're providing a better environment for their employees, tailored to their actual, real-time behavior. They've stopped bleeding energy to cool empty chairs and ventilate vacant rooms. They are applying power with the precision of a surgeon, not the brute force of a sledgehammer. This ability to see and count the people inside is transformative. It turns the building from a static, rigid box into a dynamic, responsive organism. But as powerful as this is, it's still only reacting to what's happening inside its own walls. It's an internal awareness. The next evolution, the truly mind-bending step, is when the building starts to look outside. What happens when your HVAC system stops just reacting to the present moment and starts predicting the future? What if it could look at tomorrow's weather forecast, see a massive heat wave coming, and start making a plan to deal with it tonight while everyone is asleep? This is the fundamental shift from a reactive machine to a proactive, intelligent partner. This isn't science fiction. It's a strategy called predictive load management, and its most powerful weapon is something called pre-cooling or preheating. And the secret to how it works isn't just in the fancy computers. It's in the building itself. Think about your building for a second. It's not just an empty box of air. It's thousands of tons of concrete, steel, glass, and drywall. All of that material has what's called thermal mass. It can absorb and hold on to heat, or cold, for a very long time. In a traditional building, this is a passive quality. But in a smart building, the thermal mass becomes its greatest asset. The Smart HVAC system learns to use the entire building structure as a massive, rechargeable thermal battery. Let me explain, because this is the single biggest game changer. Imagine a scorching July day is on the forecast for tomorrow. A traditional HVAC system does nothing until tomorrow morning when employees start arriving and the thermostats start climbing. Around 10 a.m. as the sun gets stronger, the AC kicks on. By 2 p.m., with the sun at its peak and the office full of people and computers, the system is screaming at 100% capacity, desperately trying to fight a losing battle against the heat. It's an energy disaster. All of this is happening during peak demand hours, when electricity costs the most. You're paying premium prices to run your most expensive equipment at its absolute maximum. Now let's see how the smart system plays chess while the old system is playing checkers. The smart system sees that same 95-degree forecast. But instead of waiting, it makes a plan at 10 p.m. the night before. It sees that between 2 a.m. and 5 a.m., electricity prices are at their absolute lowest. The outside air is also at its coolest. So it begins to run the chillers, not to make the air icy cold for an empty office, but to gently and efficiently pour coolness into the building's thermal mass. It's slowly charging that thermal battery. The concrete floors, the steel beams, the core walls, they all begin to absorb and store that cold energy. When the sun comes up the next day, the building is already preconditioned. It's not just the air that's cool, the very bones of the building are cool. As people arrive and the day heats up, the building's structure acts like a giant thermal sponge. It passively absorbs the heat generated by people, lights, computers, and the sun beating through the windows. The thermostat doesn't spike. The AC doesn't have to roar to life. Instead, it might just hum along at 30 or 40% capacity, sipping energy instead of guzzling it. It has effectively shifted its heaviest energy load from 2 p.m., the most expensive time of day, to 3 a.m., the absolute cheapest time of day. This strategy is called peak shaving, and for a commercial building, it is the holy grail of cost savings. Here's why. Most people think their commercial electric bill is just based on how much energy they use, the kilowatt hours. But that's only half the story, and often it's the smaller half. A massive portion of a commercial bill, sometimes over 50%, comes from something called demand charges. A demand charge is a fee based on the single highest spike of energy usage during a billing period, usually measured in 15-minute intervals. Think of it like your cell phone bill. The kilowatt hours are like your total data used. The demand charge is like a massive penalty for downloading a huge file at the busiest time of day, which slows down the network for everyone else. The utility company charges you a premium for that peak moment of stress you put on the grid. And here's the killer. That one 15-minute spike at 2 p.m. on the hottest day of July can set your demand charge for the entire month. You could be incredibly efficient for 29 days, but that one afternoon of peak usage defines your bill. A traditional HVAC system is a demand charge creating monster. It waits for the hottest moment of the day, and then turns everything on to full blast, creating a massive, sharp spike on your energy graph. A smart, predictive HVAC system does the opposite. By pre-cooling the building, it flattens that curve. It replaces that sharp, expensive afternoon spike with a long, low, cheap overnight ramp-up. It avoids creating that peak, and in doing so, it can slash those demand charges by 30, 40, even 50% or more. We're not talking about saving a few bucks on the light bill. We are talking about erasing a huge chunk of one of the largest operational expenses a building has. And this isn't just for cooling. The exact same logic applies in the winter. Instead of blasting the heat at 7 a.m. on a frigid Monday morning when the building is ice cold, the system will look at the forecast on Sunday night. It will see the cold snap coming and begin to slowly and efficiently preheat the building's thermal mass during the cheapest off-peak hours overnight. So when employees arrive on Monday, the building is already radiating a comfortable, base level of warmth, and the main heating system only needs to do minimal work to maintain the temperature. This predictive power is driven by an incredible fusion of data. The system isn't just looking at the public weather forecast. It's pulling in hyperlocal weather data, sometimes from its own on-site sensors. It's analyzing the building's historical performance data from thousands of previous days to understand exactly how this specific building reacts to a certain temperature, humidity, and solar load. It integrates with the utility company to get real-time electricity pricing signals, so it knows precisely when energy is cheapest. And it knows the building's occupancy schedule. It knows that on Tuesdays the accounting department is full, but on Fridays half of them work from home. It's not just a thermostat. It's a data scientist, an energy trader, and a facilities manager all rolled into one autonomous platform. It stops treating the building like a dumb box that needs to be constantly force-fed energy and starts treating it like an active, dynamic asset. The building itself becomes part of the solution. By turning tons of concrete and steel from a passive problem into an active thermal battery, the system fundamentally changes the economics of heating and cooling. So we've turned the building into a thermal battery to fight the weather. But what about the people inside it? What if the HVAC system knew exactly where every single person was and where they were going next? And what if it could use that information to create a perfect bubble of comfort that follows them around the building, while letting empty spaces just fade away? That's not science fiction. That's the power of sensor fusion, and it's where this gets really personal. Sensor fusion isn't about having more sensors just for the sake of it. It's about creating a single hyper-aware consciousness for the building. Think of it like an orchestra. A single violin is nice, but a violin, a cello, a flute, and a percussion section playing in harmony? That's a symphony. In our building's orchestra, the occupancy sensor is the violin, playing the simple melody of "someone is here." But then the CO2 sensor joins in, the cello adding the deep, resonant note of how many people are here and how long they've been breathing in that space. You see, every time you exhale, you release carbon dioxide. In a poorly ventilated room with a lot of people, that CO2 level skyrockets. It's the reason you feel sleepy and unfocused in a stuffy 2-hour meeting. Your brain is literally being starved of oxygen. A smart HVAC system uses these CO2 sensors not just to count people, but to measure the actual quality of the air they're breathing. When it detects a spike in CO2 in conference room B, it doesn't just guess. It knows it needs to pump in a precise amount of fresh, oxygenated outside air to maintain peak cognitive performance for the team inside. It's the building's way of breathing in sync with its occupants. This isn't just about comfort, it's about productivity. And it's incredibly efficient because it's not flooding the entire floor with fresh air, just the single room that actually needs it for the exact duration it's needed. Then the humidity sensor, the hygrometer, joins the performance. This is the flute, adding the high nuanced notes that truly define the feeling of a space. We've all said it. It's not the heat, it's the humidity. You can have 2 rooms both at 72 degrees Fahrenheit. One with low humidity feels crisp, cool, and comfortable. The other with high humidity feels like a Louisiana swamp in August. Sticky, oppressive, and miserable. A smart system understands this intimately. It knows that by actively managing humidity, by pulling that excess moisture out of the air, it can make 74 degrees feel as comfortable as 71. And let me tell you, those 3 degrees are a gold mine. For every single degree you can raise your thermostat in the summer, you are saving a significant percentage on your cooling costs. We're talking about a potential 3 to 5% savings per degree. In a large commercial building, that's not pocket change. That's a new employee's salary. That's a budget surplus. All because the system was smart enough to tackle the humidity, not just the heat. But the orchestra is still building. The ambient light sensors are the percussion setting the tempo. They detect the intensity and position of the sun. As a brilliant beam of sunlight streams through the east-facing windows in the morning, the system doesn't wait for the thermostats on that side of the building to start screaming for help. Sees the sun coming. It knows that a massive amount of thermal energy, free heat, is about to be dumped into that zone. So it proactively dials back the heating in that area, or even begins to push a gentle stream of cool air to counteract the effect before it even happens. It's the difference between a firefighter reacting to a blaze and a fire marshal preventing the fire from ever starting. One is costly and chaotic, the other is silent, predictive, and efficient. This fusion of data creates a living, breathing picture of the building. It's no longer a collection of dumb zones. It's a dynamic, shifting mosaic of microclimates. Let's make this real. Meet Sarah, a graphic designer who works on the 15th floor. The system, integrated with the building's security, notes when Sarah swipes her badge at 8:55 a.m. It knows her assigned workspace is in the northeast corner. Using a combination of anonymized Wi-Fi data and thermal occupancy sensors, it confirms her arrival at her desk. Sarah, like many designers, runs multiple high-performance computers and monitors that kick off a lot of heat. The system knows this. It also knows that her corner of the building gets blasted by the morning sun. So the VAV, the variable air volume box that controls airflow to her specific zone, makes a micro-adjustment. It pushes a little more cool air her way, while simultaneously reducing airflow to the empty desks just 20 feet away. Sarah just feels comfortable. She's able to focus on her work, unaware of the silent, intelligent symphony playing out above the ceiling tiles. A symphony that is saving the company money by not overcooling the entire corner of the building just for her. Now let's scale that up. The main boardroom. a massive space with floor-to-ceiling windows designed to impress clients. It's also an energy hog. For 90% of the week, it sits empty, a ghost of a room. A traditional system would have to keep this room at a general standby temperature, a compromise that wastes energy when it's empty and often fails to cool it down fast enough when a big meeting starts. People end up fanning themselves with papers for the first 20 minutes. A smart system, however, integrates with the company's digital calendar. It sees that a 25-person board meeting is scheduled for Wednesday at 2 p.m. The system does nothing all morning. The room sits in a deep, energy-saving setback mode. But at 1:30 p.m., the AI calculates the current temperature, the outside temperature, the solar gain from the afternoon sun, and the heat load of 25 human bodies. It runs a million tiny calculations and determines that it needs exactly 28 minutes to bring the room to a perfect 71 degrees with fresh, low CO2 air. So at 1:32 p.m., it awakens the massive air handler dedicated to that zone. The VVs open, cool air begins to pour in, and when the CEO walks in at 2 p.m. sharp, the room feels perfect. Not cold, not stuffy, just right. The moment the meeting ends and the sensors detect the room is empty, it begins to ramp down, returning to its energy-sipping slumber. That is surgical precision. That is the elimination of waste on a grand scale. Now, I know what some of you are thinking. Tracking employees? Isn't this a little Big Brother? It's a valid concern, and it's the first one that needs to be addressed. These systems are designed for building efficiency, not employee surveillance. The sensors are tracking anonymous heat signatures and CO2 plumes. The Wi-Fi and Bluetooth locators are only tracking the presence of a device, an anonymous MAC address, not the person holding it. The system doesn't know or care that you're John from accounting. It only cares that a heat-producing, CO2 exhaling entity has entered a zone that now requires conditioning. It's about managing BTUs, not people. The goal is to make John more comfortable and productive so he can do his best work, all while slashing the operational cost of his workspace. It's a win-win. This fusion of data, this symphony of sensors, gives facility managers a superpower, omniscience. They can see in real time how their building is being used, where energy is being wasted, and where the opportunities for optimization are. It transforms their job from constantly reacting to comfort complaints to proactively fine-tuning a high-performance environment. They are no longer just building managers. They are conductors of this incredibly complex and beautiful orchestra. So we have this incredible symphony of data, a constant stream of information from a dozen different sources, all flowing together, painting the most detailed, high-resolution picture of a building's life ever conceived. But who is the conductor? What is the brain that takes this beautiful, complex chaos and turns it into a masterpiece of efficiency? That brain is not human. It's something far more powerful, and it learns. It's an intelligence forged not in flesh and bone, but in silicon and data. The brain of the modern smart building is artificial intelligence, specifically a branch of it called machine learning. And its sole purpose, its entire reason for existence, is to learn every single secret your building has to tell. Now, I know what you might be thinking. AI? Isn't that just a fancy word for a complicated computer program? For years, that was basically true. We had building management systems, or BMS. Think of a traditional BMS as a very strict, very literal-minded orchestra conductor. It has a single piece of sheet music and it follows it perfectly. The sheet music says, at 8 a.m., turn the temperature to 72 degrees in Zone A. At 5 p.m., set it back to 78. It does this every day without fail. Monday, Tuesday, Christmas Day, the day of the solar eclipse. It doesn't matter. It follows the rules. It has no ability to improvise, no capacity to understand context. It can't look at the audience and see they're getting restless. It just plays the notes on the page. This AI-driven brain is not that conductor. It's a master jazz musician. It knows the fundamentals, the chords, the scales, that's its base programming. But its real genius is in its ability to listen, to feel the rhythm of the room, and to improvise a unique masterpiece in real time. It doesn't just follow static rules. It creates dynamic strategies. How? Through the power of prediction. A traditional system reacts. It waits for a room to get too hot, then blasts cold air. It's always a step behind, constantly playing catch-up, and wasting enormous amounts of energy in the process. A learning system predicts. It lives in the future. Let's take weather. Your old system knows one thing, the current temperature outside. The AI brain knows that. but it has also ingested the entire day's forecast from multiple meteorological sources. It knows a heat wave is rolling in at 2 p.m. It knows the cloud cover will be thick until noon, then break. It knows the humidity is projected to spike at 4 p.m. It cross-references this with a mountain of historical data from inside your own building. It knows from thousands of previous days exactly how your building's west-facing wall responds to direct afternoon sun. It understands the building's thermal inertia, how long it takes for a change in outside temperature to actually affect the inside. So instead of waiting for the 2 p.m. heat wave to hit and then frantically cranking the AC, the most expensive and inefficient way to cool a space, the AI starts making subtle adjustments hours in advance. It might begin pre-cooling the core of the building at 11 a.m., when electricity is cheaper and the system doesn't have to fight against the sun. It lets the concrete and steel act like a thermal battery, storing the cool. By the time the heat wave arrives, the building is already prepared. Just needs to maintain, not panic. It's the difference between a fire alarm and a fire prevention plan. One is a reaction to disaster, the other is the intelligence to avoid it altogether. This predictive power extends to the most unpredictable element of any building: people. Your old system runs on a fixed schedule. It assumes everyone arrives at 9 and leaves at 5. But we live in the real world. A world of hybrid work, flexible schedules, and half-empty offices on a Friday. Heating and cooling empty cubicles is like watering a garden full of plastic plants. It's pure waste. The AI brain sees this. It integrates with every data stream we talked about. It sees from the Wi-Fi access points that the third floor is only at 20% capacity today. It sees from the CO2 sensors that the main conference room, usually empty on a Tuesday, is suddenly packed. It might even have access to anonymized calendar data, knowing that a big client meeting is scheduled for 1 p.m. So what does it do? It diverts resources. It pulls back on conditioning the empty sections of the third floor, saving that energy, and pushes it to the crowded conference room, ensuring everyone stays comfortable and alert. It's not heating a building, it's conditioning for people. It turns your HVAC from a blunt instrument into a surgical tool, applying comfort exactly where and when it's needed and nowhere else. But here's where it enters the realm of financial genius. This AI doesn't just know about weather and people. It knows about money. It is constantly monitoring the energy market. It knows in real time the fluctuating price of a kilowatt hour. In many parts of the country, electricity costs more during peak demand hours, typically in the late afternoon. The AI sees this. It treats the energy grid like a stock market, and it is the ultimate day trader. It knows a price hike is coming from 4 p.m. to 6 p.m. So at 3 p.m., when electricity is still cheap, it executes a strategy called load shifting. It pre-cools the building, dropping the temperature a degree or two lower than normal. Then when the clock strikes 4 p.m. and prices skyrocket, it eases off the compressors. It lets the building stored cool do the heavy lifting, coasting through the most expensive part of the day. The occupants never notice a difference in comfort, but the utility bill? The utility bill notices. It's a game-changing strategy that a static, rule-based system could never even conceive of, let alone execute. And this brings us to the most crucial word: learning. This isn't a one-time setup. The system never stops learning. The day it's installed, it's the dumbest it will ever be. Every minute of every day, it's conducting thousands of tiny experiments. It's learning the unique thermal signature of your specific building. It learns that the server room needs a constant, steady stream of cooling, but the corner office with the floor-to-ceiling windows needs a powerful blast only after 3 p.m. It learns the patterns of your employees. It discovers that on Wednesdays, everyone goes out for a team lunch from 12 to 1, and it can scale back the system during that hour, saving money every single week. It refines its own algorithms based on what works and what doesn't. It's in a state of perpetual optimization. It's a digital facility manager that never sleeps, never takes a vacation, and is obsessed with one thing: finding every possible efficiency to save you money while maximizing comfort. This transforms the very idea of a building. It ceases to be a passive, dumb container of concrete and glass. It becomes a living, breathing organism. The sensors are its nervous system, feeling every change. The HVAC equipment is its respiratory system, breathing life and comfort into the space. And the AI is its conscious mind, a mind that anticipates, adapts, and learns. It's a mind that turns chaos into harmony, waste into savings, and a simple structure into an intelligent environment. But this intelligence, this brain, is only as good as the body it controls. How does this digital mind actually command the massive, powerful machinery, the chillers, the boilers, the air handlers that form the muscle of the entire operation? How does a line of code translate into a perfectly cooled room? That connection between the digital brain and the physical world is where the magic truly happens. That connection between the digital brain and the physical world is where the magic truly happens. It's a complex dance of sensors and actuators, the unsung heroes of the smart HVAC revolution. Think of it like a biological system. Your brain makes a decision. Pick up that glass of water. But how does that thought become action? Your nerves send signals and your muscles contract and move. In a smart building, the sensors are the nerves, and the actuators are the muscles. The sensors are the eyes, ears, and fingertips of the building. They are constantly feeling, measuring, and reporting back. Thermostats measure temperature. Humidistats measure moisture. CO2 sensors measure air quality. Occupancy sensors detect if people are in a room. They are the frontline data collectors, feeding a relentless stream of information back to the Central Building Automation System, or BAS. But data is useless without action. That's where the actuators come in. An actuator is simply a device that makes something move. It's a small motor, a valve, a piston. It receives a digital command from the BAS, a string of ones and zeros, and translates it into physical motion. It opens a damper to allow more air in. It closes a valve to restrict the flow of hot water. It adjusts the pitch of a fan blade. The actuator is the physical hand that carries out the brain's command. Let's walk through a real-world scenario. Imagine a corner office on the sunny side of the building. It's 2 p.m., the sun is beating down, and the temperature starts to creep up. The thermostat on the wall, our sensor, detects the change. It doesn't just know it's hot. It knows it's precisely 75 degrees Fahrenheit, 3 degrees above the desired set point of 72. It sends this tiny critical piece of data to the BAS. The BAS, the central brain, receives this signal. Its programming, the complex algorithms we talked about, instantly kicks in. It analyzes the data. Zone 14B is 3 degrees over set point. Action required. Then sends a command. This command travels through the network to a small, unassuming metal box in the ceiling above that office, called a VAV box, a variable air volume box. Inside that VAV box is an actuator connected to a damper, which is like a metal flap inside the air duct. The command from the BAS tells that actuator, open the damper by 40%. The small motor whirs to life, turning a gear that pushes the damper open. Suddenly, a greater volume of cool air, supplied by the main air handler, begins to flow into the corner office. But it doesn't stop there. This isn't a dumb on-off switch. It's a constant feedback loop. The thermostat continues to report the temperature. As the cool air fills the room, the temperature drops. 74 degrees, 73 degrees. Finally, it hits the 72-degree set point. The thermostat reports this new data. The BAS receives it and sends a new command to the VAV box actuator. Modulate the damper back to 15% open. Just enough to maintain the perfect temperature, not enough to waste energy overcooling the space. Now multiply that single action by 1,000. In a large commercial building, you have hundreds, maybe thousands of these zones, all with their own sensors and VAV boxes. One conference room is packed with people, getting hot and stuffy. Its CO2 sensor and thermostat send alerts. The BAS commands its VAV box to open wide, pumping in fresh, cool air. Meanwhile, an empty storage room on the north side of the building is perfectly fine, so its VAV box is commanded to close almost completely, saving energy by not conditioning a space that doesn't need it. This is zone-level control. But the real genius of a smart system is how it aggregates all this information to control the massive, energy-guzzling central equipment. The BAS isn't just a traffic cop for individual rooms. It's an orchestra conductor for the entire building. It sees that 200 of the 500 VAV dampers are now more than 50% open. It understands that the total demand for cooling has just increased significantly. So, it sends a command to the giant air handler unit, or AHU, up on the roof. It tells the massive fan inside that AHU to speed up. It does this using a variable frequency drive, or VFD, which is like a highly sophisticated dimmer switch for a giant motor. Instead of running the fan at 100% speed all the time, the VFD allows the BAS to ramp it up to, say, 70% speed, exactly enough to meet the building's current demand and not announce more. This alone saves a staggering amount of electricity. The cascade of logic continues. The air handler is now working harder. which means it needs more chilled water to cool the air. The BAS is monitoring the temperature of the water returning from the air handler. As the building gets warmer, the return water gets warmer. When that water temperature crosses a certain threshold, the BAS makes its next big decision. It sends a command to the heart of the entire system, the chiller plant. It might decide to increase the output of the currently running chiller, or if demand is high enough, it will stage on a second chiller. It makes these decisions based on complex calculations to ensure it's always running the plant in the most efficient configuration possible. This reactive control is incredible, but modern smart systems are taking it a step further. They're becoming proactive. The BAS can now be integrated with external data feeds, most importantly, the weather forecast. The system doesn't just know what the temperature is right now. It knows there's a heat wave coming tomorrow. It knows that by 3 p.m., it's going to be 98 degrees and humid. A legacy system would wait until 9 a.m. tomorrow, when employees are arriving and the building is already starting to bake, and then it would have to fire up the chillers at 100% capacity, drawing a massive amount of power during peak daytime hours when electricity rates are the most expensive. A smart system thinks ahead. It sees the forecast and formulates a plan. At 2 a.m., when the building is empty and electricity is cheap, it will start to gently pre-cool the building. It runs the chillers at a low, efficient level for several hours, slowly pulling the temperature of the building's entire thermal mass, the concrete floors, the steel beams, the drywall, down a few extra degrees. By the time the sun comes up and people start arriving, the building itself is a giant, cool battery. The HVAC system doesn't have to fight a losing battle against the sun. It only has to maintain the comfortable temperature it already established. This strategy, called peak load shifting, can slash a building's utility bill by avoiding those exorbitant peak demand charges. And the intelligence doesn't end with energy savings. It extends to the health of the equipment itself. This is called fault detection and diagnostics, or FDD. Your car has a check engine light. A smart HVAC system has a check engine light for every single component. It's constantly monitoring thousands of data points: motor amperage, fan speeds, valve positions, water pressures, refrigerant temperatures. It learns the normal operating parameters for every piece of equipment. It knows that a specific fan motor should draw 12 amps when running at 80% speed. One day, it notices that motor is now drawing 15 amps at the same speed. It's not broken yet, but something is wrong. A bearing could be failing or a belt could be slipping. The system automatically generates a work order for the maintenance team. Alert: HU5 supply fan motor amperage 25% above expected value. Recommend inspection. The technician can now replace a $50 bearing next Tuesday, instead of having to replace a $5,000 burned-out motor during an emergency call on a Saturday. The system can detect a slowly leaking valve that would have gone unnoticed for months, wasting thousands of gallons of chilled water. It transforms building maintenance from a reactive, firefighting-based model to a proactive, predictive, and data-driven one. This intricate web of communication, from the tiniest sensor in an office to the most powerful chiller in the basement, all governed by intelligent, forward-thinking software, is the engine of modern efficiency. It's a system that not only responds to the present, but anticipates the future, not only controls the climate, but also protects its own components. It's this deep, interconnected intelligence that unlocks the truly massive savings we've been talking about. But how do you actually put a number on it? What's the real return on investment? Let's break it down using a real-world, albeit hypothetical example. Imagine a mid-sized commercial office building. Let's call it the Innovate Tower. It's about 50,000 square feet. With its older, conventional HVAC system, the building's annual energy bill for heating and cooling is a staggering $100,000. That's not uncommon. For many businesses, HVAC is their single largest operational expense after payroll. The facility manager is constantly fielding complaints. One department is freezing, another is sweating. The maintenance team is playing a constant game of whack-a-mole, reacting to breakdowns and replacing parts as they fail. Their capital budget includes a massive line item for a full system replacement in the next 5 to 7 years, a cost they are dreading. Now let's install a smart commercial HVAC system in the Innovate Tower. We're talking the full suite: variable speed compressors, smart thermostats, occupancy sensors in every zone, CO2 sensors for demand-controlled ventilation, and a cloud-based building automation system that ties it all together with predictive analytics. The upfront cost for this retrofit is, let's say, $150,000. That number might make a CFO's eye twitch. seems like a huge expense. But this is where we stop thinking of it as an expense and start analyzing it as an investment. First, let's look at the direct energy savings. Based on countless case studies from the Department of Energy and private firms, a smart system like this can realistically cut HVAC energy consumption by 20 to 40%. Let's be conservative and say we achieve a 30% reduction for the Innovate Tower. 30% of their $100,000 annual bill is $30,000. That's $30,000 in cash, back in the company's pocket year one. And it's not a one-time saving. It's $30,000 year after year after year, for the life of the system. As energy prices inevitably climb, that dollar amount will only grow. Next, let's consider maintenance and repairs. The old system was reactive. A fan motor would burn out on the hottest day of the year, leading to an emergency call-out. That's overtime for the technician, rush shipping on parts, and the unquantifiable cost of lost productivity from uncomfortable employees. With the new smart system, the AI is monitoring the vibration signature of that exact same fan motor. It detects a subtle change, a pattern that indicates the bearings are beginning to wear. It automatically creates a low-priority work order for the maintenance team. A technician replaces a $10 bearing during scheduled downtime next Tuesday. The catastrophic failure, the emergency call, the expensive motor replacement, and the office-wide disruption, it never happens. This proactive, predictive maintenance doesn't just prevent disasters. It optimizes the maintenance budget. Let's conservatively estimate that this saves the Innovate Tower another $10,000 a year in reduced emergency repairs and optimized labor. So now we're at $40,000 in annual savings. But we're not done. The single biggest line item in any long-term HVAC budget is capital replacement. A conventional system run hard and inefficiently might last 15 years. But our new smart system is a finely tuned orchestra. It avoids the harsh, damaging cycles of constantly slamming on and off. The variable speed drives ramp up and down smoothly. The system self-diagnoses and protects its own components from undue stress. This extends the operational lifespan of the core equipment. Instead of lasting 15 years, the new system might reliably last 20 or even 25 years. So that massive replacement cost we were dreading? We just pushed it 5 to 10 years further into the future. The time value of deferring a multi-$100,000 expense is a massive financial win, freeing up capital that can be invested back into the business's growth. Now let's do the math. We have $40,000 in direct, measurable savings each year. The upfront investment was $150,000. If you divide the cost by the annual savings, you get a payback period of just under 4 years. 3.75 years to be exact. Find me another guaranteed low-risk investment in your business that delivers a 26% annual return. You'd be hard-pressed to find one. After year 4, that $40,000 a year is pure profit, directly improving the building's net operating income, and by extension, its total asset value. But the true return on investment goes far beyond these hard numbers. This is what separates a good decision from a game-changing one. Think about the tenants of Innovate Tower. With granular zone control, every department is now comfortable. The marketing team can have it a little cooler, while the accounting department, which is always cold, can have it a bit warmer. The conference room, which used to be an icebox for 2 people and a sauna for 20, now automatically adjusts its ventilation and temperature based on the number of occupants and the CO2 levels. What does this do? It dramatically impacts employee productivity and well-being. Study after study has shown a direct link between thermal comfort, proper ventilation, and cognitive function. When people aren't distracted by being too hot or too cold, and when their brains are getting fresh, properly oxygenated air, they are more focused, more creative, and more effective. They take fewer sick days. This isn't a soft benefit. It's a direct boost to the most valuable asset any company has. It's people. How much is a 5% boost in productivity across an entire company worth? It dwarfs the energy savings. Then there's the brand. In today's world, corporate and social responsibility isn't just a buzzword. It's a critical factor in attracting top talent and customers. The Innovate Tower is no longer just an office building. It's a smart, green, sustainable building. It can now proudly market its reduced carbon footprint. It can achieve LEED or WELL building certifications. It becomes a physical manifestation of a forward-thinking, modern company culture that has real, tangible value. So how do you get there? How do you take your building from being a reactive energy hog to a proactive, intelligent environment? It's a 3-step process. First, you need a benchmark. You can't manage what you don't measure. This starts with a professional energy audit. A qualified firm will analyze your building's current systems, your utility bills, and your building's envelope to identify the biggest areas of waste and the greatest opportunities for improvement. This gives you a data-driven starting point. Second, you develop a strategy. It doesn't have to be an all-or-nothing rip-and-replace scenario. For some buildings, a phased approach is best. Maybe you start by upgrading to smart thermostats in a basic control system. You prove the ROI on that smaller investment, and then you use those savings to help fund the next phase, like upgrading an aging rooftop unit to a variable speed model. For others, a full retrofit during a planned renovation makes the most financial sense. The key is to have a long-term plan tailored to your specific building, budget, and business goals. And third, and this is the most critical step, you choose the right partner. This is not a job for a standard residential HVAC technician. You need to work with commercial contractors and engineers who specialize in modern building automation systems. They understand the complexities of integrating different pieces of equipment. They know how to program the control logic to maximize both comfort and efficiency. They are partners who will not just install the hardware, but will help you analyze the data and continuously optimize your system's performance over time. Ultimately, this entire conversation is about a fundamental shift in perspective. For 100 years, we've treated our HVAC systems as a necessary evil, a dumb brute force utility that sits on the roof or in the basement, burning cash every minute of every day. That era is over. A smart commercial HVAC system is not a utility. It is a strategic asset. It is a financial tool that can dramatically lower your operating costs. It is a human resources tool that can improve the health, comfort, and productivity of your people. And it is a risk management tool that future-proofs your building against rising energy costs and evolving environmental regulations. The question is no longer if you can afford to upgrade to a smart system. In the face of what's coming, the real question is, how much longer can you afford not to? The technology is here. The data is clear. The return on investment is undeniable. It's time to stop just heating and cooling your building and start making your building work for you.